Hi everybody, I'm going to talk about enolate reactions in this video. So this one's going to specifically cover the aldol and the Claisen reaction. It is important to note that aldol, I capitalized it here and here just because I'm using it as like a heading. But aldol is not a person's name. It's not capitalized if it's just kind of a word in a sentence. It's just a combination of aldehyde and alcohol. So it's not anything, it's not a proper noun or anything, it's not capitalized. Claisen is a person's name. That Claisen reaction is capitalized, but it's a really common thing. Like people think that the aldol is a person. It is not. It's just aldehyde and alcohol. Again, because organic chemists love just shoving words together. And along those same lines, the aldol reaction is when an enolate reacts with a ketone or an aldehyde of itself. So in the previous video, we talked about that equilibrium at play where you had both the ketone and the enolate present in the flask at the same time. When those two things react, that is the aldol reaction. So what it makes is it makes conjugated enones or enals. Okay, so we're looking at this as the enone. And again, that's going to be a ketone that's conjugated with an alkene, or the enal, where we've got something like this. Okay, so we're looking at enones or enals as our final product for the aldol reaction. Okay, so what does the aldol reaction look like? Let's just take a look at the simplest one between acetone. So if you take acetone and you throw some base in it, maybe heat it up a little bit, you can get this reaction to occur. So if I have sodium hydroxide here, I'm going to leave my space for to put the product over there. So our first step is going to be that enolate formation, okay, with sodium hydroxide. So we're going to go grab our alpha proton, form our enolate. And in this case, you can draw whichever enolate form you prefer. So I will show you how to do both of them. Yeah, I'll probably do it on the next one. So on this one, I'll just use the reactive form. And then on the other one, I'll do the more conjugated, the major resonance contributor, and show you what the mechanism looks like with that. But it's very, very similar. So once we have that enolate, we're going to go ahead and we're going to react it with another molecule of acetone that has not been turned into the enolate. So we want to keep in mind we have about 50-50-ish of enolate and ketone here. So we're going to go attack that carbonyl just like we've done with all the other carbonyl reactions. And at this point, we need to number. I don't know exactly what it is about aldols, but they are just notorious for making you lose your carbons. So numbering here is going to be probably even more important than it is normally, which is saying something because it's pretty important. So we're making a bond between 3 and 5, and then we've got 4 and 6. Okay, and we also have that O- over here. So once we have that O-, we did just make water in the previous step, and I'm going to try to do my equilibrium arrows here and remember that. Okay, so we can get to this, which is our aldol addition product. Okay, this is generally tough to isolate because we haven't yet kind of hit a bit of a thermodynamic sink, and we'll talk a little bit more about that in just a second. Okay, it's very likely to just kind of fall back apart and get back to acetone from this aldol addition product. Okay, so once we're here though, we technically still have acidic protons around and we're technically still in base at this moment. So what can happen is we can have our hydroxide come in again, and this alpha position is still acidic. So we can deprotonate right here, form another enolate. But instead of that enolate going and reacting with another molecule of acetone, it can do something now intramolecularly so that we have something that can happen pretty quickly. And it can just go and form an alkene right here and kick off that hydroxide as a leaving group. So we normally say, you know, hydroxide is not a great leaving group, but we do need to keep in mind here, we are already in base. So we have quite a bit of hydroxide around, and we're also getting ourselves to a much more stable product, and that we're forming this conjugated system afterwards. Okay, so this conjugated system is much lower in energy. So we're really going to think about this as kind of our irreversible step of the aldol reaction. Okay, it's really tough to isolate it without having this final step. So most of the time with aldols, we're going to assume that we get to here if we're using kind of OR minus bases. Okay, and I just want to write this down to remember that not all the acetone gets turned into the enolate. Okay, that's what makes this whole thing possible. If we had a completely irreversible 100% conversion process going here, we would not be able to actually do this reaction because we wouldn't have any of this left. All right, so then let's talk about a more complicated situation. Let's talk about the crossed aldol. So a crossed aldol is just when you have an enolate reacting with a different carbonyl than itself. And it's specifically going to be a ketone or an aldehyde. Okay, so when we're looking at this, we're thinking about the fact that if we had, you know, something like these two, we could have a really big mess just because of how many alpha positions we have and how many options we have for enolates and electrophiles here. So to make this keep us with high selectivity and get a good single product out of it, there's a couple things, a couple tricks that we can use. So first, we can kind of differentiate between really good electrophiles and less good electrophiles. So if we use a ketone for the enolate, and pair it with a better electrophile. Okay, a really good electrophile in this case would be an aldehyde, right? So if you use a ketone, it's generally going to turn into that enolate more so that it can react with that more reactive aldehyde. So that's one way to do it. The other thing to keep in mind is if you minimize the number of alpha positions you have and alpha protons, that helps a ton. Okay, so if you have a situation where, you know, you kind of have cut yourself down to having just one option, you know, this is a good example because we only have one alpha position with protons on it. And then we have kind of these two things combined where we've got one ketone that only has one alpha position, and we've got an aldehyde. So those are going to give us a pretty good selectivity for this product. Okay, where we're getting something like that. So those two are really key. And if none of those are working out for you, the other thing that you can do is you can preform the enolate with LDA. Okay, and we need to remember from the first video that when we use LDA, we're getting 100% conversion to the enolate pretty much every time. And you're not going to have any of that carbonyl left over. So if you do that, you just kind of add your LDA, you wait a while, and then you add your electrophile. That can get you out of a lot of problems, okay, a lot of trouble. So an example of that one would be if we had, you know, this ketone, and we first used LDA, and that's going to give us that irreversible step right off the bat. Okay, and then we dump in our electrophile that we want to use, and let's say we want to use acetone here as our electrophile. I got it all smushed. So then we can have our enolate come and attack, push that up. And the interesting thing about this is that since we have LDA, we don't have water present. So we're actually kind of stuck here. And this allows us to actually be able to isolate the aldol addition product if we would like. So if we quench this, we can actually isolate this. Or we can add some acid and some heat and essentially just do like an E1 elimination. Okay, if we'd wanted to do that as well. So with LDA, you can isolate the aldol addition. But we can also use acid and heat to get to the conjugated enone or enol. Okay, but there's definitely kind of some tips and tricks that you can use if you're in a crossed aldol type situation. All right, so let's look at the Claisen reaction. So this one, we're going to see a whole lot of similarities here between the aldol and the Claisen. So the difference here is that this is an enolate that reacts with an ester. Okay, so as always, we have kind of very similar but slightly different variations when we have ketones and aldehydes versus esters here. And this is going to make 1,3-dicarbonyls for us. Okay, so that's going to look like this, where we've got 1, 2, 3. That's going to be a 1,3-dicarbonyl. That's what we're looking for in terms of the products of a Claisen reaction. So let's start off with an ester. So this is ethyl benzoate. And then we'll go ahead and bring in cyclohexanone again. Okay, we'll use NaOET. Again, we're matching this to whatever our ester is to make sure that any kind of transesterification there just happens internally without us really registering it. First step, we got to form that enolate. Again, that is a reversible step. So we will have, some of the ketone present, but you can also do stuff in terms of concentration to make this the more accessible option and kind of push things to completion that way. So then that enolate, oh, right. I didn't do it on the last one, so I'm gonna do it this time. So this is how you can do it from the major resonance contributor. If you want to use this enolate, this is totally fine as well. You can just show this coming down to form a pi bond, and then that pi bond is going to go to your nucleophilic attack, right? Either option is fine. I don't care which one you use. If you like to use this enolate form, go for it. If you want to use this one, also fine. Okay, so then that is going to get us to this intermediate. And I'm going to try very hard to keep myself straight over here. Okay, making sure that we're not losing any carbons along the way. So then this does exactly what you would expect a ester to do, right? It wants to reform the pi bond, that carbonyl bond, and I have a leaving group present. So we're going to kick off that leaving group. Okay, I made more OET minus. Again, this is another really good reason that you have matching bases with your esters. And then from here, it looks like we're kind of done, but we want to look at this really carefully and notice we have a really acidic proton right there, right? Because that proton is in between, two carbonyls. So that's going to be a pK of about 9. So our base is immediately going to go grab that proton. Oops. And once we have that taken, we formed basically a really, really stabilized enolate. Okay, so this is actually the final product of this reaction. And this is the irreversible step that we need to actually be able to isolate any product. Okay, so far we've kind of seen irreversible steps in that the aldol forms that conjugated enone as its conjugated step. The LDA aldol, that first deprotonation is the irreversible step. And then for the Claisen reaction, it's this kind of last deprotonation that's our irreversible step. And then once we're here, we really can't get there without an acid quench. Okay, so this is just going to be stable until we quench. Because there's much, much more reactive enolates being formed here. So this one isn't going to really do anything once we get there. So once we have an acid quench, though, then we can go ahead and protonate that. And then we formed our 1, 2, 3, 1,3-dicarbonyl. Okay. So if we don't have that irreversible deprotonation step at the end, You won't be able to isolate product. Okay, so we got to think about that really carefully and making sure that we always have one proton left over here to be able to do our final deprotonation and then get to the end. Oh, and I forgot to add the ethanol over here. And again, that pKa is 16. So that's how we get that irreversible step. We got that big pKa difference. So as always, let me know if you have any questions, and I will see you all later.